Okay.
Now we're rolling.
Okay. So maybe I should go back to say big data is exciting. Just in case it needs reinforcing. A big business, of course. Everybody, lots of advances, systems architecture, computation, but it raises the question, should research focus on these sort of big solutions to big problems? And there was a slight precedent in literature for examining this question. And of course, if you draw a business school graph, everything's increasing. This is a graph of projected big data market forecast. A slowdown. Look at the top there, projected slowdown, and this was from a market research report due to uncertainties over adoption. Should or can everybody have a supercomputer or a cluster? Do they know how to run it even? Or pay the price of entry for that? So should we just be doing big stuff, big systems, big business, everything sort of feeding each other? Or, and one way you can think of this as a lot of work, and this is not to disparage it, but it is finding ingenious ways of throwing resources at problems. Which seems to make sense as long as you don't have to pay too much for things. But maybe we're just addicted to resources. Just because you can doesn't mean you should necessarily. And my experience, in fact, was somewhat the opposite. That in fact, part of the reason we do research is to actually, we start with big data and then try to render it smaller. And instead of just saying we're committed to working with big stuff, let's do work which enables us to trade off between exact and approximate answers, bigger versus smaller data, faster versus slower. And of course, this is a great opportunity for people like me who are analytically minded. And we had a lot of success with this approach in network research at AT&T, where we had some huge data sets, but effectively we rendered them small and useful, and sort of exploring the approximate smaller, faster axis of this trade-off. Of course, ISPs are a great place to do big data research. A lot of questions there have been around for a while, demand for solutions, and in fact there was a lot of success in actually getting solutions into services and routers. So let's look at the structure of a large ISP network where we have city-level routers connected by backbone links, all kinds of access networks hanging off them. There are many operational data sets associated with this. I'm going to just focus on one that I wrote in IP traffic flow measurements. These are generated by routers. Summaries of transactions of data. We'll talk a little bit about, in more detail, because the setup for that in just a minute, what are these flow records, what are IP flows. But just to say, generally, I see three challenges at the ISP level for data analysis. The scale, of course, some of these data sets are big. For example, traffic measurements, there is data on mobile device handovers. A standard thing to do is compute and analyze summaries, and we'll talk a bit more about how you do that. And that's basically, we're going to talk about scale mostly in this talk. But I just want to mention the two other challenges as I see them. Incompleteness. Not all quantities can be directly measured, so what we have to infer what we want from what we have. We can't measure performance on every link. We can measure end-to-end performance. Can we infer link performance from end-to-end performance? Complexity. We have the interactions between networks, protocols, traffic, people, and the statistical properties of these are very difficult to model. And we have noisy or missing data, heavy tails, correlations, and so forth. Okay, so those are sort of three challenges, and I think they recur in a lot of settings. Why are we going to summarize data? Well, in the ISP context, we might have limited transmission bandwidth to get our data from the measurement point back to where we analyze it, although that's not so much of an issue nowadays. More question is limited storage. It's infeasible to accumulate raw data streams. I'll talk about the size of these in a minute. At least can we maintain historical summaries for baselining if we want to do some kind of anomaly detection? If we want a fast query response, well, it's unfeasible to run exploratory queries over full data. I'm drawing the distinction between exploratory queries and canned queries where we just have pre-defined aggregates. If I want to explore the data, how much traffic was going from here to here at this time using these protocols. If it wasn't a canned query, I need to explore my data. And I want the answer, in a couple of seconds rather than over lunchtime. And one way to approach that is as part of a hierarchical query infrastructure. Even if you can't maintain your raw data indefinitely, at least maintain it over some period, construct some summaries, drill down through those summaries, maybe multiple layers in these summaries to get your answer. So that's why summarize. Why is sampling a good way of summarizing? Well, sampling has intuitive semantics. We obtain a smaller data set with the same structure, if we sample correctly at least. And estimating on a sample is often straightforward. You can run the tools you have on the sample that you would run on the full data, but try and get your answer quicker. And we'll see that some form of adjustment, rescaling, reweighting of the surviving sample points may be necessary to do things like unbiased estimation. Sampling is general and agnostic as a method, at least, to the analysis that must be done. Other summary methods, aggregation, plenty of different sketches and summaries only work for certain types of computation, although it turns out we do need to tune sampling to in a way that makes us better able to answer the queries of interest. And sampling is usually easy to understand. We start off with these objects, we end up with a smaller set of objects which are representative. It's easy to communicate about. I see sampling as a sort of mediator of constraints. On the one hand, we have these data characteristics, for example, heavy tails, correlations, and we have our resource constraints, bandwidth, storage, CPU, or if we're going to say, I can get these resources out in the cloud, it still comes at a cost. And our query requirements. We want to do exploratory ad hoc queries, we want them to be accurate to a certain degree, and we want them to be returned quickly. So sampling sort of is a method to enable us to negotiate these sort of three constraints. So let's go back to this picture of traffic measurements, in particular flow records from routers. So what is a flow record? Well, what's a flow? Well, a flow is a timeline where we have illustrates a set of packets observed at a router, and an IP flow is a network-level view of a user session. It's a set of packets with a common property called a key observed close together in time. And this key is what distinguishes the packets of one connection, for example, in TCP from another. Common IP and source destination, common IP source and destination address, TCP, UDP ports, and so forth. Protocol numbers. So flow records are protocol level summaries of individual flows of packets constructed from the packet headers, not the content typically, continuously compiled by routers and then exported either in-band or out-of-band to a collector. And these summaries have the flow key information, packet and byte counts, timing information, the first and last packet, and so forth. And these are used to manage the network over a range of timescales, from capacity planning over timescales of months to detecting network attacks over timescales of seconds. And to scale this, well, many hundreds of terabytes of flow records per day, at least if you didn't do anything to control the volume. In terms of data rate, that's not particularly high. In terms of data storage, it's starting to get up there. Well, let's take this picture and recast it in a language which you all understand. Keyed data streams. So in this data model, my objects are keyed weights. So each object is characterized by a key and a weight. So the weight x would be, for example, the number of bytes in the flow or the number of packets in a flow. And k is the flow key, the common endpoints of the packets. And so we're given a stream of these keyed weights, n of them, and we're interested in a generic query, which I'll phrase as a subset sum. So in other words, I have some subset S of my index set, And I'm interested in knowing the total weights of all the packets whose index lies in that index set X. And typically, my index subset S would be the set of all packets whose key, all packets I, whose key K sub I falls in some set big K of interest. So for example, big K could represent the set of all keys flowing from a particular IP address to a network using a particular destination port, also observed within a particular amount of time. And so what I want to be able to do is, from the point of view of summarization, compute a fixed size summary of this stream that can be used to estimate arbitrary subset sums with known error bounds. So the point here is I'm including the case that I don't know what K is at the time I do the measurement. If I did, I could just aggregate over K. Your question?
Would you always look for sums which are indexed by capital K, as opposed to, I want to find the largest weights, the flow. So this is not, this is basically defined by the weight as opposed to the key.
Right.
Would you be interested in those kinds of questions?
Yes, I could have that as a selector as well.
What do you mean by fixed size? Does it depend on n?
Yes, it could. I mean, generally it would, in the sense that if I have a given accuracy target, the size of my sample will depend on the number of points I have. So, well, there's a general framework in which to describe sampling and estimation operations for inclusion sampling. So this was formalized by Horvitz and Thompson, and the idea is if you have an object of size x sampled with a probability p, I have an estimate of x, which is I divide, if I sample the object, I divide x by p, and if I don't sample it, well, my estimate is implicitly 0 because it's not there in my sample set. This is unbiased because if I take the expectation of my estimator x prime, and then with probability p, it's x over p, and with probability 1 minus p, it's 0. So I get an unbiased estimator. And if I'm interested in estimating the subset sum, well, by linearity, the estimate of a subset sum is the sum of the corresponding estimates. So in other words, if I want to estimate, if I have a particular subset sum I'm interested in, x of s, then I can form an estimate of this just by adding up the corresponding unbiased estimates of the items in the sample that also lie in S. So that's what I mean by x prime of s. And in schemes like this, you typically have exponential bounds, so the probability that x prime s deviates from the true value xs by some multiple delta of the true value is bounded by some exponential quantity, which is exponentially small in the size of the object you're trying to estimate, and some constant, which depends on depends on how you're doing sampling and the size of the deviation you're interested in. And you can translate this into confidence intervals for xs. I mean, notice here this bound is in terms of xs, the thing I'm trying to estimate for a start, but you can actually turn that around to say, well, for a given measurement, x prime of s, what's the probability that x of s lies outside a certain interval, and make that suitably small. Okay, so we're going to talk about instances of this scheme. I talked about in that triangle picture I drew, I talked about the need to match data and analysis with sampling. So let's consider two generic problems, one of which is counting objects and here we just have a weight, the weight of every object is 1, so we're just counting objects. And here we have uniform sampling with probability p works just fine. We can estimate the count, where here x of s is just the count of objects in S, so we can estimate the count. The unbiased estimator is just the number of my samples which lie in S, and divide that by the sampling probability. And the relative variance is basically, as you might expect, it's proportional, roughly proportional to 1 over p, so as my sampling probability goes down, my relative variance goes up, but it's inversely proportional to the size of the object time, the size xs, so as the size of the thing I'm trying to estimate goes up, the relative variance goes down. And so basically, given p, you can get any desired accuracy for large enough s. So if you look at an experiment where you're saying, well, I'm trying to estimate the count of 5,000 objects from a sample, and here's a graph of my estimated values. Everything's nice. I have this sort of, this nice comfortable behavior, which is suggestive of the central limit theorem. I can get a Gaussian approximation to the distribution, and so everything's nice. Now, of course, in general, things aren't quite as nice. We have heavy tails out there in the internet. For example, if you look at the Pareto distribution or Pareto-like distributions occur. Also, we talk about 80-20 laws. A small fraction of the objects have a large fraction of the weight, or a small proportion of the population owns a large proportion of the wealth. There are many examples of this: degree distributions in the web graph, social networks, bytes and packets per network flow, file sizes in storage was one of the first cases examined. And here we have for a set of flows, we're looking at the distribution of packets per flow. Here's the log-tail probability, and we see this roughly linear behavior, which is indicative of the Pareto distribution. Now, the consequences for that sampling are actually severe. So if we, in this sort of second generic problem, where the xi's, the weights follow a Pareto distribution, if we do uniform sampling, we're likely to omit one of those heavy objects, and that gives us a big hit on accuracy. And making the selection set large doesn't help. So here we did done the same experiment with actually a set of flow data where we have the total number of packets in the flows is 10 million, and we've done uniform sampling, and then we try to use the Horvitz-Thompson estimator to infer from the samples the number of packets. And we see, if you look at the histogram, the distribution of those estimates, and see this is on a log plot, it's far from the nice, comfortable, approximately Gaussian picture we had before. And you see, in fact, some of our estimates here are 10 times the true value, and then we have the bulk of the estimates are somewhat lower than the true value. And the point is here, if we do sample one of those big flows, now in this data set, I think there's one flow which has a very large proportion of the total packets, and if we sample that, we divide by the sampling probability, we end up with this very large estimate. If we miss it, we're down here. So maybe we should just forget about sampling and take the m largest objects, but that's biased, and small objects are systematically ignored, which is potentially a loophole from which people can squeeze their flows by splitting them up into flows which aren't measured. What do we do? Well, this is where, now they say everything has a cost, and I found this a very useful way to think about sampling. And I'm going to talk really about sort of just one instance of this, but in fact there are many different frameworks in which you can, many different instances in which you can, I found it useful to look at things in the same framework. But let's just look at independent sampling n objects with a set of weights, and each of them is going to have their x1 to xn. Each of them is going to have their own private sampling probability. And we're going to do Horvitz-Thompson estimation. And there are going to be two costs, one of which is the sampling variance of each of the estimates, which takes this form, and the other of which is the expected sample size, which is just the sum of the sampling probabilities. And so these are two costs, so what I'm going to do is I'm going to add them together and minimize the total cost. And I'm going to add them together with a constant, so a weighting z squared. And z expresses the relative importance of having a small sample versus having a small variance. Because if z squared is small, then I tend to make this cost small by making this variance term small. So in other words, p is going to be large. But on the other hand, if z squared is large, then I tend to make this cost small by making the probability small. So in fact, then I'd have a small sample size. So z is a knob where I can sort of tune to express my relative priorities. So how do I minimize cost sampling? Well, I want to minimize that cost function subject to the constraints that I have probabilities, which sum to 1. I should have written that in. And the solution is inclusion probability proportional to size sampling. So it's pretty straightforward to derive it. So the probability, the probability pi to sample object I with weight xi is the minimum of 1 and xi over z. So we call z the sampling threshold. So it's a threshold between two types of behavior. For objects which are larger than the threshold, their sampling probability is 1. So that big flow, I'm always going to get it as long as it's larger than z. And everything that's small, in the sense of being smaller than z, gets sampled with a probability that's linear in its size, proportional to its size. And if I look at this distribution of packet counts I had before, what it does is it sort of tames the heavy tail. So this is with my this parameter z, which I can tune, and it's a story I'm not going to go into as to how you actually determine what the z should be, but I'll indicate that in a little bit more detail later. But in this case, I tuned z so that I took the same number of samples. Or at least, sorry, had the same average sampling rate. And in this case, as in the uniform sampling case, in this case, we recover our nice smooth behavior. So in this, our estimates are well behaved, clustered around the true value.
So this thing you mentioned is just for a single key.
Right.
Right? Because then you also have multiple keys.
Right. So I apply this.
For every key.
Right. So I would use the same. I regard z as a parameter which I'm going to apply to every. I mean, z is a knob, so I'm going to have the same setting for every flow. I mean, in principle, I could differentiate, and the reasons why you might want to do that, but there's no need to.
Different flows may have very different characteristics.
Right.
Different slopes of the perimeter. Or I mean, different powers of the power.
Right. I mean, perhaps it's worth saying that we're not exploiting any particular form of the Pareto distribution. What we're just trying to do is something which is robust. I mean, I can apply this to in the first case as well, and I'll just get my uniform sampling. So I mean, if you had distinct populations which had labels which you could be aware of at the time sampling, then yes, potentially you could apply a different threshold to each of those subpopulations. And you might want to do that for, I don't know, for load balancing, for you might want to have some way of making sure you get representative samples from a particular subpopulation that didn't have as heavy a tail as the other guys. Okay, so there are, you could, in fact, I did one piece of work where looking at sort of using that to express various degrees of fairness in the way sampling was done. So fair question. Okay, suppose now think about this independent sampling is, if my traffic doubles, my number of samples doubles, and generally if my distribution of my flows changes, I'm going to get a different volume of samples. So, if I have a constraint on the samples I can take, then, or the number of samples I can take, from my, the capacity of my measurement system, that's not so good. So how do I take a fixed size sample? So the aim is I want to take an IPPS sample of size n from an arbitrary length stream, and here's how I'm going to do it. I'm going to provisionally Well, I'm going to start with, I'm going to do reservoir sampling, and I'm going to provisionally include items in the reservoir. So suppose I have room for m items. I'm going to take the first m. And now that's sort of the initialization, and now it sort of really starts. Because suppose I'm in a situation where I do have m items in my reservoir. When the next item comes along, I'm going to provisionally include it. And then what I'm going to do is I'm going to discard one item randomly. So to do this, I'm going to recalculate in general a threshold z which would sample from those m plus 1 items, from those 10 items, m, 9 in this case, on average. So in other words, I want z to solve that the sum of my sampling probabilities over my 10 items is m, 9 in this case. So actually, it's quite an interesting problem as to how you do that efficiently, and you can do it in, it's an order log m calculation amortized over m arrivals, but I'm not going to go into the details of how you do that. So if I calculate the threshold, then I know my sampling probabilities, the PIs, so the discard probabilities, the 1 minus my sampling probabilities, these are the QIs, they sum to 1. So what I'm going to do is I'm going to lay out on the unit line the lengths QI corresponding to each of these objects. So I should have said that here the width of each of these objects, the width of the box is equal to the weight, xi, and so you see and the weight, I partition the unit interval with the corresponding discard probabilities. So in other words, object 9, this is its discard probability. Object 8, this is its discard probability. Object 10 has a discard probability 0 because its weight is greater than z. So it gets sampled with probability 1. And so I pick a uniform random number in the unit interval, and the unlucky victim gets discarded. And then finally, I have to adjust my weights by constructing the Hurwitz-Thompson estimator, which in this case, when I divide by the minimum of 1 in x over z, is equivalent to taking the maximum of x and z. So everything that had size below z gets bumped up to z, and everything that's size exceeded z just stays as it was. Okay, so this is, I think it's interesting because this is a, oops, what's happening now? Okay, so, well, I say first of all, this is, IPVS sampling is actually, in current use. Actually, the sampling distribution was previously known, but there was no good way of performing the sampling efficiently. So the complexity of the calculation increased not only with the size of the reservoir, but with the number of samples you'd seen. So it just was not suited to streaming at all. So there was, no previously computationally feasible approach to this for streaming data. So I think, there's a larger point here that we need to, the sort of the big data question, as it were. The best results are going to draw from across disciplines. We needed statistics and algorithms to do the job. Yep.
Can you go back to your Z scheme?
My which?
The scheme for updating the Z.
Yeah.
So, okay, so every time something new comes in, you recalculate the Z.
Yeah.
And the Z is calculated so that you would keep on average.
Yes. Yeah.
From your m plus 1.
Yes.
Okay. And so that much I got, and then I didn't get this last point about readjusting the weights.
Right, so in the Hurwitz-Thompson estimation, when you do sample an object with probability p, you have to, if it survives, you have to replace the object's its size x by x prime, which is x over p, because that's the unbiased estimator.
Yeah.
So, I actually lose track of what, well, I don't need to retain what the original size of the object was. Now, for operational purposes, I may want to do that. But from the point of view of unbiased estimation, all I need to do is maintain the x prime.
So with this readjustment, would it mean that z would always increase in every step, or it would stay the same? It would never decrease.
Does Z increase? Z does not decrease.
Yeah, Z does not decrease.
Yes. Okay, so finally he talks about graphs. So, of course, graphs are really big data. And, you know, so examples are, you know, search providers, web graphs, online social networks. Well, I guess it depends which facet of the graph you're interested in. I mean, Facebook has 1 billion users, billion's not really big anymore. Trillion links, roughly, that's respectably big. In ISPs, we have communication graphs. So, for example, you know, these flow records, I can think of as links on a graph in which the nodes are the sources and the destinations, as represented by the IP addresses, or the IP addresses, the port numbers, or whatever identifier you want to use. Whatever portion of the key identifies either end of the communication. And so we have an edge if traffic flows between them, and that edge can be annotated with properties of the flow, the amount of traffic, the timing information, and so forth. And so I think of, you know, just as we have internet service providers, I think of a graph service provider. So, you know, we want to have fast, retrospective queries over graphs, which may, you know, have multiple layers of different information. So, for example, we can think of an IP communications graph, but we also have social networks. We have external information not related to these measurements at all, but some other set of measurements, how people are using resources. And so, of course, there's a great industry in how we link these things together. And the idea of sort of following on from, you know, the motivation in the internet measurement, that sampling needs to be representative over the set of required objects, the set of objects that we're interested in, whether it's a set of interesting nodes, links, paths, subgraphs. So how do you do sampling how do you sample the right things? Briefly put. Of course, we've got lots of interesting examples talking about social networks, the internet, bioinformatics, blogs, but all these have been looked at. Let's think, you know, for example, if we're thinking of a streaming graph in an ISP. So here we have a graph which is in which the nodes are IP addresses, source or destination IP addresses, and we have a stream of edges, these flow records arriving. Think of these as directed edges, representing a flow from a source to a destination node. So let's have a look at, you know, the most recent entries in our database. So here's one flow. Oh, here's another flow, and another, and another, and then I noticed there's a set of flows which happens just about at the same time, where this node is sending traffic or exchanging traffic with the destination nodes of these flows, and then suddenly these start sending an enormous amount of traffic to this node here. So, well, this is a botnet, or maybe it's a flash crowd. But I can think, well, in this case, you know, this type of behavior, this sort of scenario happens where we have, you know, a compromise of a set of hosts, and then a control message went out, which led to flooding. And so the questions here are, well, one trouble is, you know, it's going to be hard to detect this against the background, because if we just had these flows, we'd say, of course, it's a botnet. But in fact, there are all the other flows going on in the network. If we know what the attack looks like, we could do signature matching based on, you know, partial graphs or flow features or timing information or some combination of those. If there are unknown attacks, it would be nice to do sort of exploratory and retrospective analysis, just in the way we did we enabled using the non-graph flow sampling. But to do that, you know, we have all the same questions. You know, if we're sampling, how do we preserve the accuracy if we're trying to estimate, for example, the frequencies of these events? So, I mean, this brings on us to the problem of sort of streaming subgraph estimation, which is quite a hot topic at the moment. There's been a lot of work, including ours, focused on sample-based methods to triangle counting from graphical streams of edges. And people are focused on triangles because it's the simplest, non-trivial representation of node clustering. If you can't do triangles, you can't do that far harder problem, which I don't claim to have a solution of right now in dealing with the network attacks. But at least if we can develop things which work on this prototype, we can try extending them. Of course, just as we found in the previous case, uniform sampling performs poorly. The chance, if you have a large graph, the chance for a random sampled edges to form a subgraph in your sample set is approximately 0, so you sort of have this exponential decay in the size of the subgraph. So what we need to do is do the same kind of thing as we did with when we were looking at the flow records. Let's bias our sampling. In other words, I'm using bias there to mean let's have unequal sampling probabilities. So the desired subgraph is preferentially sampled. There's been a lot of work in this. Here are just 3 papers, but some people used assumption on the arrival order of the edges in the graphs, and if you can do that, it makes, of course, if related edges arrive at closely spaced times, it's easier to sample them all. A more general approach is to just sample the edges in any case. For example, I need to sample simpler subgraphs. In this case, wedges are which is 2 edges joined, a subgraph of triangles, so one approach is to have a triangle-specific data storage which is optimized for sampling the subgraphs of interest, triangles in this case. So the approach we took was more in line with the work we've done in the flow record sampling, which is to say, let's just take some sample which is selected mindful of the type of analysis we want to do afterwards, but we're going to do all the analysis we're going to do in post-processing, rather than try and build it into the way we do sampling. So here's a framework to do this. Okay, so suppose I have a stream of edges, E1, E2, and so forth, and let L sub n be the first n edges, and I get a sample some set of edges from these. So L prime n is a random subset of samples from Ln, which I'm going to sample somehow. So how do we do that is the question. But we're going to do some kind of adaptive edge selection. The idea is that the probability that we sample an edge En depends on what we sampled before, because the relevance of a particular edge depends on its adjacencies within what I've sampled. I may also try to retain some level of information about the stuff I didn't sample as well, but I don't exclude that. So this is a framework we proposed and applied in the triangle case. And from the point of view of estimation, you have a conditional version of this Horvitz-Thompson, which is, this is my edge sampling indicator. So that my indicator of a particular edge En being in the sample Ln of the first n edges, this is, by which I mean a function which is the random function, which is 1 if the edge is sampled, 0 if it's not. Then I can have a counter for this edge, which is like the Horvitz-Thompson estimator. I take this indicator function, which says, did I sample it, then divide it by the sampling probability. This conditional sampling probability, so this is, this actually depends on what happened prior to n arriving. So this is in fact a random number. But that's okay, because I'm assuming that it's determined entirely by what happened previously. I guess I should include by what happened previously, and so in that case, the conditional expectation of this counter, this Horvitz-Thompson style counter, is 1. So on average, I count the edge, but whether I do or not is a random thing. So let's see how that idea of this adaptive approach applies, for example, with wedges and triangles. So here's an edge which arrives. here's another edge which arrives, and I'm going to sample each of these edges with probability p. So p is my sampling probability for an isolated edge. Oh, that one didn't get sampled. First one I retained, the second one didn't get sampled. Then another edge comes along. It's incident to this edge I've already sampled. I'm going to sample it with some other probability q. Now another edge comes along, p. It's still like this one's isolated. I sample it with probability p, and then another edge comes along. It actually completes this triangle, so I get to sample that with some probability r. And great, I got a triangle. If I want to count that triangle, I'd better apply the correct normalization, which is the product of the sampling, the conditional sampling probabilities. So even though these are, these are sort of random quantities, in any particular sample path, I know their exact values. So the idea is by having q greater than p, I'm favoring wedges versus just independent sampling of edges. And by having r greater than q, I'm favoring triangles. In fact, you might want to set r equal to 1. Since I'm so interested in triangles, if an edge completes a triangle, I'm always going to sample it. We can actually generalize this to, because we have this, this conditioning gives us a conditional independence, which means everything's a product. So I can generalize, suppose I have a subset of edges. I can just take the product of these indicator functions over the edges, and that is an unbiased estimator of 1. So it's in fact it's a random count for the edge, and so in particular if I have a triangle, I just take the product of the random counts for those edges, and which if I when I do sample it, takes the value just run over the product. So that's just a slight formalization of what I had before.
I have a question.
Yeah.
Previous slide. So an edge might complete more than one triangle. Right. Or it might complete a triangle and a wedge.
Yeah.
And make a new edge.
Yeah.
And stuff like that.
Yeah, you can do all that. I mean, in some sense.
Then the thing is, it's not like the count estimator is not exactly correct because these things are not independent.
Well, I mean, it's true that they're not independent, but if you're just taking expectation values, that doesn't matter because the expectation of the sum is sum of the expectation. When, I didn't bother putting this on the slide, but when you want to calculate the variance of your estimators, then yes, precisely, you need to take account of those correlations there.
Maybe I should rephrase my question. Say I have an edge that's going to both make finish a triangle and make a new wedge. Yeah. What should be its sampling probability? Should it be R or Q?
Oh, that's up to you. I mean, in the sense that, I would say choose the largest one because it represents the most important thing. But that's just a policy. I mean, this is you can have these be anything you want. So it's up to you. I mean, I'm telling you what I'd do, but you can do something else. That's fine. I mean, this isn't tied to any particular choice of the probabilities.
But don't you ultimately want to say something about your estimator, that it's going to tell you something about the number of triangles you have?
Yeah.
And it does so regardless of how you choose that?
Yes, so the question, what are the statistical properties of that estimator? So I'm always going to end up with an unbiased estimator, but just as we saw with the flow counts, I mean, that sort of the bad estimator where I had uniformly sampled the flows, it was still an unbiased estimator of the byte count. It was just horrendous because it was uniform, because the variance was high.
So do you have the result on what its variance is? Like, I mean,
yes. Yeah, I didn't. The result is concerning there's an unbiased estimator of the variance. Actually calculating the variance itself is not straightforward, and we don't know how to do that.
you can numerically calculate an unbiased estimator.
You can numerically calculate an unbiased estimator, yeah.
But we could do that for uniform sampling as well.
Yes. Yeah, the point is not that I'm enabling you to do a computation you couldn't do before. The point is the framework enables you to do these computations. And so you can say, well, how do I select my particular parameters to get me the right trade-off between, estimation and variance that I want? So how does this framework actually apply when I'm doing my graph sampling? Well, I'm going to sample my edge stream with these conditional probabilities tuned to the desired subgraphs. I would say that here our results are less complete than it was in the streaming case. So I think it's an open question as to how to optimally choose your P's in some theoretical way, as opposed to an empirical way. Watch this space. But we can record the sampled edges and their probabilities, and then having done that, then we do the estimation. So you can do this, you can do this quickly with your stream, and then shunt your samples off to some other location, and then you do your estimation, because that's where you run your queries, on this set of samples. So for example, if you're interested in graph subsets and sums of graph subsets, so when I say that, this is sort of abstraction of saying, I want to count the triangles, or I want to count the triangles which have a particular edge as one of their vertices, or if I'm thinking of a case where I have annotated edges, I want to count the triangles which contain at least one edge which has this annotation in this range, whatever my selection is. Well, after I've done that selection, then I end up with some set of graph subsets, J1 up to Jn, and the size of this, the sum of the estimators for each of those subsets is just an unbiased estimator of the number of subsets in that sum. So that's what the general framework gives you. Let's do some experiments where looking at different graphs out there in the public domain. We're looking at counting edges, triangles, wedges, clustering coefficients, and we're going to look at the relative error, the estimated and actual values of these various variables, and we're going to look at upper bounds and lower bounds based on using the variance estimate. I'm trying to think the best way to summarize this. Well, on the one hand, here let's go back to we have these graphs with up to nearly 700 nodes and up to 7 million edges, and we have a sample size which is less than or equal to 40k edges. So there we've tuned the sampling probabilities to get a sample of this size, and our relative errors are less than 1% for these variables. Here's another way of putting it in terms of looking at, you see the normal sorts of behavior that you would expect in terms of let's see, let's bring that down a bit. Oops, be right back.
And how does this compare to other methods for doing triangle counting?
I'll come to that. Oops, I realized this. Oops, I thought there was something there. Okay. Okay, I thought I missed something, but no. Okay. And so here we're looking at the estimated versus the actual value from a set of experiments, and in some sense, the take-home story here is we have the nice narrowing of results as we increase the sample size to the the true value of estimated versus actual. Which one means exact. So comparison to other works. So the easiest thing to compare with was, which the results were most explicit, was the streaming triangles work from KDD 13, and there we saw significant improvement in terms of accuracy for a given sample size. This is really, it's sometimes down to the way we structurally organize things, that we don't have this sort of triangle-specific data structure. In that case, a wedge-specific data structure we use to build up the triangle. So we finesse that approach just by doing all the actual estimation and post-processing rather than during the sampling itself. Okay, so summary. I hope I made the case for sampling as an enabler for big data. Lowers the bars for resources via these trade-offs: size, speed, accuracy. In the graph stream sampling, we have this use conditional sampling to favor subgraphs of interest. A lot of the benefits of this approach come from the fact we do estimation and post-processing, which gives us improved accuracy for a given amount of storage. Thank you.
So what happens if you don't tune your P and Q optimally?
Well, then you are going to end up with more storage for the same accuracy or less accuracy for the same storage.
How much worse does it get?
How much worse does it get? I'd have to go in and check the numbers there. I can't give you a. Yeah, I'd have to check that.
For the first part, if your elements have multiple weights, is there a way to extend the result?
Yeah, it's. I think that's an interesting question in the sense that. There are a number of answers. So one of which is yes, you can have something like construct something like a sort of combined weight, which is some combination of them. But what combination should you have? How do you compare a weight for packets and a weight for bytes and so forth? So that's and it's not obvious how to do that. How to do that in general. Another point is do you need to? In some cases, weights are going to be related. So come back to the packets and bytes question. So packets and bytes are roughly proportional, roughly. And so you can use that sample I gave where the X size of packets is going to be pretty good for byte sampling and vice versa. However, for flow sampling, where the weight is 1, it's not going to be so good. Because you're in that case you're giving this flow sampling, you want a uniform weight if you want a uniform sample, so you can count the flows with the same probability. So this raises the question in my mind, a sort of a general question is how many, suppose I had a set of weights, how many, do I need, will one sample fit all, or do I have to take some smaller number of samples to kind of cover my bases? I don't have a definitive answer on that yet.